is not only my work, but many people are working together to get to where we are at now. And we have, yeah, I'm going to basically focus on the method and show you some results afterward. So, oops, you're missing some of the side of my slide. So basically, you can still get an idea of what I'm trying to show you here, even though you're missing some of the side of the slide. On the top side, you see a range of moduli that you can have, the materials that are interesting. And on the left side here, what you're seeing is the time spent depending on the technique you can use. So at Asylum Research, we are really focusing on the fact that there is no one technique that can measure every material. So we have several techniques, and we call this our NanomechPro Toolkit. That's, you have the toolkit here on the side. And from the top, you have AM-AFM technique, which you can see spans quite a large range. There's force modulation and CRFM, which is contact resonance, which they have a little bit less of a range of moduli that can cover. There's fast force mapping, force curves, and nano indentation. As you can see from top to bottom, the lower you are on this slide here, the slower you will actually obtain an image of 256 pixel by 256 pixels. So if you look from the bottom, this would probably take maybe even a day, and you can take 10 to 20 seconds to get an AM-AFM image if you're imaging really fast. Let's see how much you can see. Okay. Well, maybe we'll be able to go without seeing the edge of the slide. All right, so first of all, why are we interested in AM-AFM? Is because it's a tapping mode technique. And tapping mode, from what you heard before, is a technique that has many advantages. And one of them is that it's really fast. It's gentle, it's low noise, so you can get images as the one you've seen this morning of calcite and atomic defects on the calcite while imaging. However, there are some limitations in terms of nanomechanical properties, is that you don't have a lot of observables. We have the amplitude that we're using to acquire the topography, and we have the phase signal, which we can use to get a ratio of dissipative and conservative force tip sample interactions, but it's not more than that you can get from tapping mode imaging. So once again, the reason for it is that you were using a single single mode of the cantilever. So what we observe here on the left is A for amplitude and phase, and from there, the material properties are always there. However, they're grouped together. So we're seeing the elastic and loss modulus and the indentation, they're all there, but they're grouped together, and there's no way for us to distinguish between them. So that's one limitation of single mode AFM imaging. However, if we have more than one mode, besides having much more complicated experiment, we get double the observable. So we have the amplitude 1 and phase 1 from the first mode, and A2 and phase 2 from the second mode. Very simplified, if we just use some models, we can calculate out the indentation depth, and then we have access to the properties of the material, which are elastic, and we can go ahead and try to figure out the loss modulus of the sample. So again, single versus bimodal is that we have double the observables. Okay, well, let me just show you both of them together so you can actually see what you're missing on this side. On the left side of the slide, you see the cantilever on top that is excited with a wave. It actually goes and interacts with the sample, and we have another collection of the signal, and then now we see how the signal changed. From there on, we can get the amplitude and the phase that I mentioned in the previous slide, and we get the topography and the loss tangent of that sample. Now if we have, actually over here, if you look here, you have the first signal is sent to the cantilever, and then we need to add another signal. This is the second mode. So what we're doing is that we're keeping this one very small compared to the initial amplitude. just to make sure that they don't overlap each other. It just becomes a small wiggle on top of the first signal. So we sum the two signals together. It is sent to the cantilever. The cantilever interacts with the sample. There's some change of the signal, and then from there on we extract the information. So again, we have whatever we had when we did single mode imaging, and then from the second resonance, we can look at the shift in frequency, and then we can calculate out some mechanical properties. What you're seeing here is that I have something different than what you're used to seeing. Normally, you would see a piezo stack on top of your chip onto which the cantilever is attached. What I'm showing you here is a laser, and this is because most of the experiments that are shown here were acquired using photothermal excitation, which we call blueDrive because it's the blue laser that we're using. So I'm gonna just take a minute here to explain a little bit what it's all about. So instead of having a piezo stack on the chip, what we do is we have a blue laser going onto the, I'm sorry, I have to look here. So we have blue laser that is focused at the base of the cantilever, and this is what's exciting the cantilever to vibrate. We still have the red laser as you're used to seeing for detection. So basically a little dim, but you can see this is the cantilever, the detection laser, and then the blue laser at the base. What's happening is that as we modulate this blue laser, the cantilever starts deflecting, and this is how we can do our measurement. So the way it works is through the bimetallic effect. So if the lever is coated with gold, we have different materials, and then while it's heated, we can see oscillation. The reason we're using photothermal excitation is that it's more stable, and this is important for quantitative results. Additionally, you can move to liquid imaging, and there, if you ever did any liquid imaging with AFM, you know that it's possible, but there's some difficulties with the forest of peaks, which are just many signals coming from the whole system being excited and in liquid. So what I'm showing you here on the right side is their actual measurements. So it's a tune of the first mode and a second mode of a cantilever, and the tunes look very clean. So, okay, before I start this short movie, what you see here in blue is a tune that was acquired on the same cantilever. However, what you see in blue is the cantilever is being excited with the blue laser, and in red is what you collect as information of that same cantilever. The whole chip is excited by piezo stack. So in liquid, what happens is you collect all the vibration of the whole chip, whereas if you have just the cantilever excited, you just look at what the cantilever is doing. So what's important to notice is that as time is passing, the blue tune still looks the same, whereas in red you see that peak is moving around because everything is changing, the liquid is moving around. So this is very important. You can still easily do an experiment with this peak, for example, the red peak here. However, if you do it over time, this peak, as you've seen in the little movie here, the peak will move around, and then you're not following the same frequency anymore. So this is a big advantage of doing using photothermal excitation in liquid experiments. All right, so I'll jump into the results section. I'll show you some results that we got in the last months. I'll show you some proof that we think that our measurements are quantitative. We did some experiments to show that the settings don't change the modulus, which is what you're expecting. There's a wide range of moduli that can be probed. And we have high spatial resolution as well as some experiments in liquid. So first, this is a polymer, multi-layer polymer film. So you can think of it as just a piece of packaging that you use your regular plastic film you put on your, you use in the kitchen. So what you see is an optical image over there. So what I knew about this film is that I knew the size of, the thickness of each polymer film, and I knew what the components were. I just didn't know what was the order. So what we did is we did some AFM imaging on it, and you can see that we were able to see different contrast on each polymer, and we were able to ID all of them. What's interesting to notice is that loss tangent, which was something you could easily get just from single mode, regular tapping mode imaging, shows you the difference between the polymer that's in the middle, but you don't see really the difference between the two polymers that are on each side. And even though the image is a little bit dark, you can see that the polymers are different. So the way we want to analyze this is that we first took a reference sample of polystyrene tin film, we imaged it, and then went ahead and imaged this sample, and we were able to separate all of the components of this film, and we're able to get some relative moduli out of this, which is very interesting because even though it's a range that's pretty small, and it's not necessarily easy to differentiate between these polymers. In this image, what I wanted to show you is that I showed you first the polymers, but here we're looking at a sample that is much stiffer. It's a silicon wafer which was covered, patterned with titanium stripes. So you can see the stripes are going diagonally. So the color that you're seeing is actually me varying the amplitude set point. So I'm changing the set point during the image. And as you see in phase, you also see these horizontal stripes, which is just me changing the imaging settings. But if you go ahead and calculate the modulus, you can clearly see that the modulus is not changing during the time of experiment. And you see that in orange you have silicon, and in blue are the titanium stripes on the sample. And if you do a histogram on the bottom there, you can see that we are able to differentiate between the two materials very, very well. So there's a wide of moduli that can be probed. So we're not limited only to very soft or very stiff materials. I'm showing you here on the left is a polystyrene polycaprolactone tin film. So in yellow is the polystyrene matrix, and then you have the polycaprolactone inclusions, and then some more polystyrene in the middle. So you can see that besides having two polymers together, you see a lot of small features, and during the whole experiment you can also see the modulus of the sample, which is interesting. In the middle there is a tin lead sample, and what I'm showing you here is actually the topography. So the topography doesn't look that interesting. And what we noticed is when we did the actual analysis, when we looked at the modulus, we saw these domains. So I don't know exactly which one, I don't know exactly what's going on in the sample. It's really just solder that I squeezed under between two mica sheets to have it flat, and we're able to see probably the tin-rich and lead-rich domains in this sample. And again, the titanium silicon sample that I showed you in the previous slide. So I just want to stress that all of these samples can be imaged with the same type of cantilever, even though the samples are very different stiffnesses. What we really were interested in as well is the high spatial resolution that we can obtain with AM-AFM imaging. So what I'm showing you here is a polypropylene sample. It's a syntactic polypropylene, so it's not very regular. What you see on the right side of the slide is the topography image. It's a 1 micron scan. You see all these crystallites kind of disordered. I had no control on how they arrange on the surface. This is spin-coated film, so they kind of arrange as they want to during the evaporation of the solvent. On the left side here is just a graphic of an old paper where people were interested in what's actually going on when polypropylene arranges in the crystalline domains. And there are some values that are associated with what should be the spacing between the samples. So what we did is we tried to zoom in. The previous image was 1 micron. This is about 55 nanometer scan. And in topography, we don't see much. We know that there are some of the crystallites. What you start seeing when you look at the frequency is, you can see more clearly on the right side, all these little spots, which are actually probably the polymers that are arranged in some kind of regular pattern. We looked at the spacing, and the spacing between these are correlating with what we saw in literature. So this is actually really interesting because this is done in air, so you don't need much preparation. You take your spin-coated film. It's done with a regular AFM tip, so nothing special. You basically put your sample in the system and start imaging and go just zoom in until you see the features. So since we got these nice images, we said, okay, well, polypropylene is interesting, but it's not so interesting to people who actually study polymers. So we try to look at, they should say polyethylene. Polyethylene is a much smaller polymer, and what we learned is that it arranges in these really regular crystalline regions when you shear it. So basically you put some polyethylene onto the surface and you shear it, and then this is how you form these regular crystallite areas. So on the right side here you have the topography. Again, this is pretty zoomed out, around a half a micron image. And when you start zooming in, this is 80 nanometers. Again, topography doesn't show much. You know that there are some high areas and low areas, but it's when you start looking at the frequency that you can see very regular arrangement of the polymer chains. And once again, the numbers that are that are reported in literature are between 0.7 and 0.9 nanometers, and this is about the spacing that we're seeing. So we're actually very excited about the fact that we can go ahead and image these polymers without any special prep. What we're currently looking at is, if you look, this is the area which is the crystalline part, which the polymers are really nicely aligned, but what you're seeing here is actually the amorphous part of the polymer chain. So it's coming out of this crystalline structure and going and kind of being amorphous before it goes to another crystalline area. So this is actually something that is of interest of people who do research on these polymers. Okay, this would really you would see nice, more dramatic if there was a little bit more contrast, but this is an image obtained in liquid, and it's DNA. It's done in AM-AFM mode, and again, you can a little bit more contrast. You can see in frequency, we can clearly see the banding of the DNA polymer that was just deposited on the surface. But since I'm going to move to the next one, since you couldn't see much. So from the first slide, if you remember, I mentioned that there's many techniques, and there's depending on the time you have, and it can take more or less time to get quantitative results if you, for example, do force curves. So this is what I want to really focus on, is the fact that you can go really fast and still get quantitative results. You can do a regular 1 Hertz scan and you get a nice image like the first one on the left there on the top. You can go faster, 2 Hertz. And this image on the bottom on the left, we're going 10 Hertz, and it's still, you can see still the same contrast. And you can even see, what I mentioned before is you can see some some crystal light. So you're still even though you're going really fast, you're seeing the contrast in modulus, but you're also seeing the small features of the sample. And when you start going really fast, 26 hertz and 78 hertz, you start seeing kind of the cantilever cannot deal with going so fast, but you're still keeping the contrast. It's only in the last image when I show you that it starts falling apart and we're not tracking anymore. So this technique is really a technique which allows you to get quantitative results fast. So this is one of the, I feel like one of the most important slides is that this is a technique which is tapping mode. So we're not pushing into the surface very much. So your sample must be clean. On the top, you have a clean sample. It's, again, the silicon titanium sample. On the bottom, you have a dirty sample. So even though you get topography in both cases, once you come and try to do, modulus, you need to have a clean sample. If not, what you're measuring is basically the thin film of dirt you have on your sample. So there's some tricks in terms of getting your sample clean and setting your tunes exactly to what they should be. But besides that, it's almost as easy as tapping mode imaging. So on that, it's a small summary of what I showed you. And yeah, if you have any questions, I'll be happy to try to answer them.
Great, let's thank Marta. We'll start on the side, questions. Okay, yes.
So what kind of resolution in, say, loss or storage modules can you get with this? Can you separate, say, something with 10 gigapascals versus 15 gigapascals, with 10 versus 12?
The question is about the resolution in modulus. So what sort of modulus separation can you resolve?
So in theory, you should be able to resolve quite a bit. All these calculations are done based on frequency shifts. So in theory, you should be able to resolve a lot. Now in practice, I'm just going to say what I was doing is, looking for, let's say, half a gigapascal in terms of polymers. That's easy to see. Another example, we're looking at, I guess, to better answer your question, if you're looking at two samples that are close together in the same family, like in the same range, you probably have much more luck than going from looking at half a gigapascal and 100 gigapascal. Although you will see contrast, getting the right modulus will be difficult because you have to think the modulus is always a calculated value and it has to do with models. So it's hard to model a tip contact that is very different depending on the sample.
Have you looked at samples that have similar Young's modulus, where one is elastic and one is viscoelastic, like, for example, octene branch polyethylene that would have, say, a 16 or 18 megapascal modulus, and polybutadiene, similar molecular weight, that has an 18 megapascal modulus, but its tan delta is on the order of 0.6, as opposed to the polyethylene tan delta is on the order of barely 0.1.
The question is about elastic versus viscoelastic materials with similar moduli.
So we did a little bit of that, but we haven't tried enough to actually go ahead and one example is some rubbers. We can see differences and we don't see it maybe in the frequency image, but we see it in the dissipation image. So this is, I guess, addressing your question. But we have to do a bit more to be comfortable with the calculation that has to be done in order to get the modulus. So that takes more time.
All right, yes.
For the AM-AFM, does the blueDrive all give you anything? I'm not talking about in water, I'm just talking about in air. Does it value anything as far as AM-AFM versus just mechanically driving those two frequencies?
Sorry, the question is about whether photothermal excitation is better than mechanical excitation in air for this specific application.
So I want to say yes, unless you're using, we have high frequency cantilever holders, which are piezo stacks that are damped. So you get better results than with a regular piezo. Now, between piezo and blueDrive, what blueDrive gives you, even if it's in air, is it's very stable and very reproducible. So what's important in AM-FM measurements is that you start with a frequency, you do your tune and you start at a certain frequency, and then you image your sample. And what you use to do the calculations is actually the shift in frequency. So if you're able to really precisely say what was your initial frequency and then see how it changed during the measurement, then your modulus value that you calculate will be more precise or more exact. So yes, I think that using blueDrive, you get a more precise reading from the beginning. So you might get a more exact number for your modulus. But in terms of having relative modular values, I think it should be the same.